Arrhenius theory of acids and bases. An acid is a compound which, when dissolved in water, dissociates to produce hydrogen ions as the only positively charged cation. Now H plus is a bare proton and cannot exist in free state in aqueous medium. Rather, it combines with polar water molecule to form hydroxonium ion or simply hydronium ion. According to this theory, bases are substances which produce hydroxide ions in aqueous medium. This theory has some limitations. Consider the gas phase reaction. The above reaction is a reality and is a typical acid-base reaction. None of the reactants are in the aqueous phase, and ammonia gas has no hydroxide ion. In fact, HCl gas has a polar covalent bond and has no replaceable hydrogen ions in the gas phase. Note that HCl has replaceable H plus ions only in aqueous phase due to dipole-dipole interaction between an HCl molecule and a water molecule. So, according to the Arrhenius theory, this acid-base reaction is happening without the involvement of any acid or base. The Arrhenius concept had to be renewed to give place to the Bronsted-Lowry theory. According to this theory, an acid is a proton donor and a base is a proton acceptor. This theory covers all the acids and bases defined by Arrhenius, or in other words, all the Arrhenius acids and bases are Bronsted-Lowry acids and bases as well, as we all know that hydroxide ions are proton acceptors. In NH3HCl gas phase reaction, the NH3 acts as a base because the lone pair on nitrogen accepts a proton. Conjugate pairs. Consider an acid or a base reacting with water as follows. Here, hydronium ion and ammonium ion are acids because they are capable of donating proton. Acetate ion and hydroxide ion are bases because they can accept a proton. Every acid or base has a conjugate pair. The conjugate base of acetic acid is acetate ion and the conjugate acid of ammonia is ammonium ion. Note that water behaves as a base when reacting with acid and behaves as an acid when reacting with a base. Thus, water is amphiprotic, a term almost similar to amphoteric. Amphiprotic substances can donate as well as accept protons, whereas amphoteric substances can react like acids as well as bases. According to this, all amphiprotic compounds are amphoteric, but the reverse is not true. Now look at the reaction between ammonia and boron trifluoride. The lone pair in the sp3 hybrid orbital of the nitrogen atom in ammonia attacks the empty p orbital of boron in boron trifluoride to form a coordinate bond. Let's play the animation and see. Here, ammonia is reacting like a base. Still, we cannot call it a base in the light of Bronsted-Lowry theory. So, in the same year, that is 1923, Gilbert N. Lewis forwarded his theory of acids and bases. According to this theory, an acid is an acceptor of electron pair, whereas a base donates an electron pair. This does not contradict the Bronsted-Lowry theory. In the above reaction, acetic acid is a Bronsted-Lowry acid because it donates a proton. But how can it be a Lewis acid? How is it accepting the electron pair? It is accepting it like this. Similarly, hydronium is an acid because it accepts electron pair like this. One thing we must keep in mind that if the acid is strong, then its conjugate base is weak, and if the base is strong, then its conjugate acid should be weak. This can be easily proved by the laws of chemical equilibrium, which say that the dissociation constant of the forward reaction is the inverse of the dissociation constant of the backward reaction. So if the acid ionizes more, the conjugate base will obviously ionize less. We have now a clear conception about what is actually an acid or base. Now the question is, what is an alkali? An alkali is a compound which is water-soluble base and gives hydroxide ion in aqueous medium. Here both NaOH and K2O are alkalis because they are soluble in water and produce hydroxide ions thereof. But zinc hydroxide and ferric hydroxide are insoluble in water. They are bases because they undergo reaction with acid. Thus we may conclude that all alkalis are bases, but all bases are not alkalis. Now, while dealing with Bronsted-Lowry acids, we need to classify them. One type of classification is based on the number of replaceable hydrogen ions the acid have. If the acid has one replaceable hydrogen ion, then they are called monobasic acid. If the acid has two replaceable hydrogen ions, then it is called a dibasic acid, and so on. This is what we call the basicity of an acid. For monobasic acids, the basicity is 1. For dibasic acids, the basicity is 2, and so on. When the basicity of acid is more than 1, then they are called polyprotic acids. Another type of classification is based on whether the acid compound has oxygen in it or not. The acid compounds having no oxygen like HCl, HCN, etc. are called hydracids, whereas the acid compounds which has oxygen in it like H2SO4, HNO3 are called oxyacids. The oxyacids are further classified on the basis of the oxidation number of the central atom of the oxyacid. The normally available acids which have a fairly high oxidation number of the central atom are called ic acids, example sulfuric, nitric, chloric acids. If the oxidation number of the central atom is lesser than ic acids, then they are called us acids, like sulfurous, nitrous, chlorous acids. There are two more. Central atom having oxidation number less than us acids are prefixed with the word hypo, like hypochlorous, hypophosphorus acids. Central atom having greater oxidation number than ic acids are prefixed by the word per, like perchloric acid, persulfuric acids. One most important thing about oxyacids is that the replaceable hydrogen atom in such acids is not directly linked with the central atom. Rather, they are attached to the central atom through the hydroxyl group. If, however, any hydrogen atom is directly linked to the central atom, then they do not add to the basicity of that particular acid. Phosphorus acid is a dibasic acid, despite it has 3 hydrogen atoms. This hydrogen atom does not count. Another important thing we should keep in mind that oxygen is attached to the central atom either by a double bond or a coordinate bond. Oxyacids having oxidation number the same on the central atom are distinguished on the basis of water content. They are prefixed by words like ortho, pyro, and meta. Orthoacids lose water to form pyroacids, which again lose water to give metaacids, which in turn lose water to give acidic oxides.